All right, everybody, we're going to get started now. So just as an introduction, my name is Grace. I go to Rich High School and I'm part of the Logistem program, not program, but today I'm going to be hosting this workshop and we're going to be covering the topic of ecology. And in case anybody is wondering, all of the recordings will be posted on the Logistem website once all of the workshops in this session are completed. So let's get started. Let's start by defining ecology. So ecology is basically, it's the study of relationships between living organisms and their biotic and abiotic environment. So something biotic or a biotic factor is a living component of an environment. For example, grass, which is like a plant, or birds, which are animals. And an abiotic factor is something that's non-living and it's part of an environment. For example, water, or soil, or like wind, things like that. And the study of ecology is important because it helps us understand the functioning of ecosystems, and it's basically the conversation of biodiversity and the management of natural resources. So there are a few population trends in ecology, and 4 of the basic ones would be exponential growth, logistic growth, boom and bust cycle, and predator and prey population, which is less of a trend, just more of a pattern. But exponential growth is basically exponential. If you know what that is, it's when the graph goes up and it begins to increase faster and faster. And exponential growth occurs when the growth rate is always going and it's not slowing down, which means that there are few things stopping this species from growing. And we'll go over those things soon. Logistic growth is basically exponential growth, but it includes results of limiting factors, which we'll go over soon. But basically, limiting factors are things that keep a population in check. They'll stop a population from growing forever, which is more realistic in our life. The boom and bust cycle is when a population exceeds its carrying capacity, or K, as it's denoted often in science. And a carrying capacity is basically the total mass of the species that can exist in its environment, in its habitat, before it runs out of resources. So the population will go up and then all of a sudden it will drop because they've run out of resources. And then the predator-prey population is like an oscillating logistic growth, because the prey population will increase and then the predator population will also increase. But then the predator starts to eat the prey, so the prey population will decrease. And then since there are less prey, there's going to be less predator as well. So you'll see how the two populations are intertwined and connected. So let's start with taking a closer look at exponential growth and logistic growth. So as you can see in the image or the graph, the first one would be exponential growth. And you can see the population size over time, it keeps going up and it seems like nothing's stopping it. But at one point, the population will reach its carrying capacity, which you see in the second one, the logistic growth. And it doesn't quite reach the carrying capacity, and that is because of limiting factors. So limiting factors, as you can see defined, are factors in the environment that prevent or limit growth. So these factors will stop or attempt to stop a population from reaching its carrying capacity, because when a population reaches its carrying capacity, it becomes dangerously close to exceeding it. And at that point, it would drop, as we'll see in the next pattern. So for limiting factors, there are different types, and one of them would be a density-dependent factor, which is something that's dictated by the density of the population. For example, predators and food. So food is an easy example, because when there's more of this species and the population is more dense, there's going to be more competition for food. It's a very limited resource. And so therefore it depends on how many of the species there are. Another type of factor are density independent factors, which are exactly what they sound like. They're the opposite. They're basically factors that are not dictated by strength of a population or the density. And these would be examples like disasters, climate change, deforestation. So for example, in a natural disaster, let's say a tornado comes through. The tornado it'll destroy everything. It'll destroy everything, no matter if there's a lot of species or just a little. So in that case, it's independent from the density of the population because everything would be destroyed anyway. Moving on to boom and bust cycle, we're going to define carrying capacity again, or K, and it's the maximum number of individuals of a species that can be sustained in a habitat without harming the environment or depleting its resources. So basically the first part is super important because it's just like actually what carrying capacity is, and the second part of that definition would be what happens if you exceed the carrying capacity. And that's exactly what happens in a boom and bust cycle. The species will go through exponential growth, which is the boom part of the cycle, and it'll reach a certain point where it has crossed the carrying capacity, or the K, and then at that point the species will like dramatically and very quickly decrease, which is the bust, as you can see in the graph. And that's because the nutrients are depleted and it's harmed its environment. And basically this is a normal life cycle for some organisms like insects, but for a lot of species you want to avoid exceeding the carrying capacity because you could cause serious damage to the environment. Okay, finally we have the predator-prey population, and this is similar to logistic growth. It's just, like I said, more of a pattern than a separate pattern by itself. And this is going to be an oscillating logistic growth because it goes up and down, which basically oscillating, it's like going back and forth. So as you can see in this example of the lynx and the hare, we have the lynx that will go up first, and then the predator follows. It'll also increase because the prey, which it eats, has increased. So now there's more food for this species. So since there's more food, there's going to be more predators. But now, because there are more predators, there's more prey being eaten. So now the prey population is going to decrease. And then since the prey population has decreased, the predator population will also decrease. And it'll go back and forth like that, with the predator following the prey with a slight lag due to time. So now let's move on to niches. So an ecological niche is basically everything in the environment that the species needs or does. It's their role in the environment, essentially. It includes what they're eating and who is eating them and where they live. And some specific things related to niches are interspecific competition and interspecific competition. So the difference between the two is that interspecific competition is between the same species. So let's say two foxes both eat hares, and now that's intraspecific competition because it's the same species and it's just two foxes that both are eating hares. And interspecific competition is going to be between different species. So for example, like cows and rabbits are both going to be eating grass. So that's going to cause both of them, which are different species, to compete for something that's the same. And interspecific competition is going to result in resource partitioning, which is the division of resources to avoid competition, and it helps species coexist. So basically, in a certain organism's niche, it's going to include a wide range of things. It's not just one role that they have, but they're going to need many different resources, and not necessarily all of them are required. So when two species are facing interspecific competition, naturally as a result, they'll shift to the separate parts of their niches that don't overlap to avoid competition to help both species exist. We'll take a look of an example right here. So as in the first graph on top, you can see the niches of the species graphed out, and you can see how there's no overlap. So both species can just play any role in their niche and take any resource that they like. If you see in the second graph, it's also having the two species niches graphed out, but in this case, there's an overlap in between. And that overlap is the interspecific competition. And the interspecific competition will push the two species to go towards the far end. So you see the blue species A, will go towards more the left side and cover whatever that part of its niche is. And species B will go more towards the right side, as you see on the graph. And that way they're trying to avoid that middle overlap, so both species can coexist in their environment. All right, now we're going to take a look at food chains and food webs. So a food chain is a linear sequence, and it'll start with a producer and end with a top consumer. And there's going to be only one species per trophic level. An example is going to be grass, and then rabbit, and then fox. A food web is similar to a food chain, but it's just many of them linked together and intertwined. And food webs are going to be more realistic than food chains because typically these kind of relationships are not linear and they're going to be very advanced and complicated. And arrows in both food chains and food webs are going to indicate the flow of energy. It's going to go from the prey to the predator. So for example, in the food chain example, you can see the arrow goes from grass to a rabbit. So the flow of energy goes from the grass to the rabbit because the rabbit is going to be eating the grass and getting energy from the grass. And the same thing applies to the rabbit with the arrow going to the fox because the fox is going to be eating the rabbit and it'll be getting energy from the rabbit. Now let's talk about trophic levels. So basically trophic levels is the position of an organism which it occupies in a food chain or food web. So producers and autotrophs are always going to be at the first trophic level. These are organisms that usually get energy from the sun, and they're going to be, for example, like grass and plants, things like that. The next level would be primary consumers, and these are going to be organisms that eat consumers. So, for example, something that would eat grass. And then in the third trophic level are the secondary consumers. So you can see like a pattern here. It goes primary and then secondary. And then the fourth trophic level is going to be tertiary. So it just follows that pattern as the consumers go up. And something important to remember is that as you go up the trophic levels, the amount of energy is going to decrease because the transfer of energy is inefficient. So when you eat something, you're only getting part of the energy that it once had. And a lot of that energy is lost in heat, so you're not getting all of the energy. So that's why the amount of energy is going to decrease as you go up. Also, the biomass will decrease as a result because there's less energy available. Therefore, less amounts of an organism can be sustained. Oh, oops. My bad. I got to the wrong slide. Oh, there we go. So the biomass is basically the total mass of living organisms in an area or an ecosystem. And this is what's going to decrease because less organisms are going to be able to be sustained since there's less energy. Now we're going to move on to age structures. Basically, these are typically related to humans. We often look at them in different countries, like developing countries versus developed countries. And these are going to show population, age, and gender distribution. So these structure graphs can be used to predict population distributions for the future. And there's three main trends that are expanding, stable, and shrinking. So in an expanding structure, you're going to see it's like a triangle shape. So there's going to be a larger part of the population that is in the pre-productive years. So children, there's going to be many more children than there are adults or reproductive humans, as you can see in this graph, defines them as between 15 and 45. And there's going to be much fewer post-reproductive people or older adults. Basically, this is because more children are being given birth to, and therefore the population is growing since there's more new children than there are adults or older adults. A stable graph is exactly what it sounds like. It's going to be relatively stable. So there's about the same number of pre-reproductive, reproductive, and post-reproductive, and there's going to be slightly less at the very top, but that's just due to natural deaths. And then in a shrinking population, there's going to be very few children, and there's going to be some amount of adults, and then a similar amount of older adults. And this is basically when a population is getting smaller. So they previously had more people, and these people had grown up to become adults. But for some reason, there's either a lower birth rate or a higher death rate in the children. So the amount of children is going to be smaller and the population is going to shrink. So moving on to taking a look how this can differ between developed and developing countries. So typically developed countries are going to be relatively stable, and they're going to like we talked about previously, have a stable and similar amount of pre-reproductive, reproductive, and post-reproductive people in their population, and generally will have similar amounts of males and females. In a developing country, they're going to have that expanding pattern, also with similar numbers of males and females. However, it's going to have much more pre-reproductive people and much less post-reproductive, because like we talked about, there's going to be more children that are surviving or more children that are being given birth to. And typically in a developing country, that's because of improved hygiene and sanitation, healthcare measures, and more opportunities for people to have their children survive, which will cause a larger number of children to be counted for since they're surviving. And now let's take a look at human demographics. So human demographic transition is the transition from an underdeveloped to a developed or industrial country. And this comes along with decreased death rates due to the industrialization, which will improve living conditions in the long term and improve the health of the population, along with better nutrition. And the human demographic transition also includes a decrease in birth rates because of improved economic conditions and an increase in women's status in education, access to contraception, and also because large families are no longer beneficial necessarily in an industrialized country. There's no need for working children, and also there are going to be child labor laws. So if we take a look at a graph here, you see how there are the yellow part, or like this orangey section, is going to represent the total population. And as this total population goes along through time, it'll increase, and it shows like this logistic growth pattern where it increases and then seems to reach this certain point, and it will slightly decrease and stay around there. So, and if we look at the green and the purple lines, you'll see how death rate is going to decrease first, because the first thing that happens with industrialization is going to be this new technology, which will help the children and the people survive. So the death rate is going to increase dramatically at first, and then slightly lagging behind it in time. The birth rate will also decrease. And so you wonder why, since even though the birth rate decreased, the population still grew. And that's because the death rate decreased dramatically. And therefore, even though less people are being born, there are many more that are surviving, as opposed to in the beginning when maybe more children were being born, but most of them weren't really surviving. And like we discussed before, the reason for birth rate decrease is oftentimes an increase in women's status and access to education and contraception. So previously, women are also oftentimes forced to have many children, and they don't really have access to education. So they oftentimes stay at home, they can't really work or go to school, and their sole role is to give birth to children and raise them. But as their status increases and they're allowed education as well as contraceptives, the birth rate will decrease as women go to school and they get jobs and work. So they're not going to be having, for the most part, these super large families that you'll see were more common. Now we're going to take a look at human impacts. So basically, humans are going to be impacting the environment in many ways. One of them is overpopulation and overconsumption, pollution, burning fossil fuels, and plastic production, deforestation, etc. So the humans are going to be, for the most part, unfortunately, impacting the environment in negative ways. And these impacts have triggered climate change, soil erosion, poor air quality, extinction, depletion of the ozone layer, undrinkable water, destruction of the coral reefs, and so many more. So human patterns of industrialization have caused a lot of these problems. For example, fossil fuels, that really started with industrialization and the Industrial Revolution. People started burning a lot more oil and coal, different types of fossil fuels. So these are a lot of things that, for example, also plastic production, that weren't really considered the long-term implications of. Like plastic is a really great resource and it's almost indestructible, it's super cheap, but nobody really considered the long-term effects that this would have, because now here we are with so much plastic everywhere. All right, so now we're going to do a little bit of practice. If there are any volunteers, there's going to be some quiz questions essentially, and you can respond to them in the chat, or I'll call on you if you raise your hand or something. Let's take a look at the first question. So we're going to be defining these factors as abiotic or biotic, if you can think back to the first definition. So the first one is sunlight. So I see Yo-Yo, you have your hand up. Would you like to reply?
Abiotic.
Yeah. So that's correct. Abiotic, and I see many people in the chat are also answering the same thing. Sunlight is going to be abiotic because it is not something living. So there we are with abiotic. Next we have trees.
Biotic.
Yes, trees are going to be biotic because they're living, and it's pretty easy since trees are clearly living. So next we have rivers.
Abiotic.
Yep, and I see also in the chat there's many people saying abiotic. Rivers are basically going to be water, which was one of the examples I said before, and water is not something that is living. All right, next we have fungi.
Biotic.
Oops. Yep, accidentally spoiled that one, but people in the chat are also getting that one correct. And fungi is biotic, even though it's not something really we think of as living, it is a living organism and it is part of the environment. And now squirrel. This one should be pretty easy.
Biotic.
Yep. And people in the chat are also getting this correct. The squirrel is going to be a biotic factor because it is a living organism. Right. And now we have wind.
Biotic.
Wind is going to be abiotic, and people are getting this in the chat as well, I see. So wind, once again, is something that is non-living, and it still impacts the environment, but it is not alive itself. All right, now we have a slightly more advanced question. So the population changes of a species is shown below. Which statement best describes the section of the graph labeled X? So I'm just gonna ask that we don't answer this question out loud for a second and think about it and type your answer in the chat. I'll give you all maybe like 2 minutes to think about this question. All right, so let's take a look at the answer. The answer to this question is going to be C. I see a lot of you put D, also some of you put D. C, which is the correct answer, but D, I see how you might think that. And it is somewhat true, but really not necessarily. Resources are high, and definitely predation is not necessarily low because you can see that the population is decreasing going back and forth. If we think back to the population trends that we covered before, this looks exactly like logistic growth, which is when the population grows and it reaches its carrying capacity, and it'll stop to prevent itself from exceeding that capacity. And there's going to be some natural oscillations after that, and it'll remain very close to the carrying capacity. So good job to the people who said C. You are correct. Let's take a look at the next question. So which population is limited by a density dependent factor? So A is a local wolf population experiences a lethal epidemic of a paravirus. B, a deer population is reduced as a result of a forest fire. C, many eggs in a population of frogs are destroyed due to a drought. Or D, a population of rams is decimated by an earthquake.
Wait, does density dependent mean like a virus or illness or something?
So density dependent, I don't want to spoil the answer, but density dependent is something that its strength is going to be depending on the density of a population. So we're going to see now that you are correct, because a virus, like we said, is something that is dependent on the density of a population. So since if you think about it, it might not be super obvious, but also many of you did say A. And that's because when this population is more dense, there's going to be the virus is going to spread quicker and it's going to affect more of the population and kill more of them. So it is something that is dependent on the density. So good job to those who said A. All right, next question. Which of the following best explains why predators and their prey have similar population cycles? And just choose one answer. All right, so I see a lot of you saying D, and that is correct. So good job, everyone. D is the correct answer because an increase or decrease in one population directly affects the other. So like we discussed before, initially the prey population will increase, and then the predator population will follow. And that is because there's more prey, and since there's more prey, there's more food available. So you can see how this increase of the prey population directly has a result on the predator population because both will increase. All right, next question. Which of the following graphs represents a population undergoing logistic growth? Answer in the chat. Give you a few minutes. All right, so I see many of you saying D, and that is correct. So basically, this looks exactly almost like the example on the slide. D is going to see an increase in the population, and then you'll see a point where it almost stops. And this one actually, it cuts off before the oscillation starts, but you can expect the population to have a slight decrease and then oscillate back and forth as it hovers around its carrying capacity. All right, moving on. A food web including 5 species is shown below. Which of the following is most likely to cause the greatest decrease in the species bee population? I see a lot of you going like back and forth. Just to help you out, the arrows are going to go from the prey pointing to the predator because that's the flow of energy.
Wait, I kind of don't get the question. Are you asking like if one species decreases, the other species also decrease?
So I'm asking from which of the answer choices, if that thing occurs, which of them would cause the species B to decrease the most?
Okay.
All right, so I'm seeing like a lot of confusion in the chat and some arguing. The correct answer is going to be D, because D is a decrease in species A. So species A, you see the arrow goes from species A to species B, meaning that the flow of energy is going to go from A to B. And if you think about the flow of energy, that basically means that B is going to be eating A and absorbing its energy. So if A decreases, then B will have less food since A is B's food supply. So if B doesn't have as much food or no food if it dies off completely, then species B will decrease. So maybe you guys were confused by the arrows or something like that, but it is the most direct cause would be if species A decreases. Oh, confused by the arrows. Yeah, that is a confusing part, but basically, no, so the arrow is going to go from the prey to the predator. So the way it's pointing is it's going to point to the predator. So B eats A and C eats B. C eats E, and C eats D, and D eats A. Yeah, so it was mentioned in a previous slide, but it is confusing if you've never really like had experience looking at these webs before. So, but option B is going to occur after B decreases, because now B is the food source for for species C. So if A decreases, then B will decrease. And if B decreases, then C will decrease, because C is going to be eating B. All right. Moving on. A food chain is represented below. Which of the following organisms is correctly paired with its role in the food chain? I'll give you all a few minutes to answer this question. All right, so the answer here is going to be C. A seagull is going to be the tertiary consumer in this food chain. So if we go through all of the trophic levels, we're going to see the first one is going to be phytoplankton, and this is going to be the producer, and it's going to be on the first trophic level. Since this is going to not get energy from another organism, and it's going to basically start off the food chain. So next we're going to have krill. If we go back to thinking about the arrow is going to go from the prey to the predator. So the krill is going to be eating the phytoplankton, and it's going to be a primary consumer because it is eating consumers. And then next we have krill having an arrow go from krill to a mackerel. And if we think about the arrows again, the mackerel is going to be eating the krill, obtaining energy from it. And so therefore it's going to be a secondary consumer because it's consuming a primary consumer. So if you count, it'll be the primary consumer is the first consumer, secondary is the second, and then seagull we see is going to be eating the mackerel because of the arrows, and therefore it's a tertiary consumer, and that's going to be the only correct pair. All right, now moving on, which age structure graph is shown below? All right, so let's find out the answer. The answer is going to be A, and this is because the population is expanding. If you look at this triangle here, triangle shape, even though you might think it's getting smaller as you go up, the overall population, if you consider this graph, is going to be expanding. This is because there's a lot more children, and because there's more children, they're going to grow up to be adults, and the overall population will increase, since that's the trend that is going on, because there used to be a smaller amount of people in the population, and that's why there's less adults and less reproductive and post-reproductive people. And now, for some reason, there's an increase in either the birth rates or there's a decrease in death rates, which has resulted in a larger population of pre-reproductive people in this population. And therefore, it shows that this population is on an expanding trend. All right, moving on. We're gonna wrap up, and that's actually the last question. So, does anyone have any questions regarding what I went over today? You can ask them out loud or type them in the chat. All right, so it seems like there's no questions for me today. That's going to be the end of my presentation. Thank you everyone for coming. Once again, there's going to be the recordings posted on the Logistem website once all of the workshops in this series are completed. So that's the end of the presentation. Thank you for coming, and you can leave now. Or if you have a question that you would like to ask, you can stay. But that's going to be it for today.
Thank you